Hi, I'm Andrew, and this is part 8 in the Advent of Code series where every day I'm attempting to solve a new code challenge. Previous videos are available on my channel in a playlist called Advent of Code 2022, and if I'm able to solve any challenge for the day, I'll upload my code to the public repository. There's a link in the description of this video. But let's get started in part 8. Today is a treetop treehouse challenge. The expedition comes across a peculiar patch of tall trees, all planted carefully in a grid. The elves explain a previous expedition planted the trees for reforestation. Now they're curious if this would be a good location for a treehouse. Probably, because there's a lot of trees. First, determine whether there is enough tree cover here to keep a tree house hidden. To do this, you need to count the number of trees that are visible from outside the grid when looking directly along a row or column. The elves have already launched a quadcopter to generate a map with the height of each tree. So that's our input is the height of each tree. Each tree is represented as a single digit whose value is its height, where 0 is the shortest and 9 is the tallest. Okay, so this is a grid. A tree is visible if all of the other trees between it and the edge of the grid are shorter than it. So, for example, 1 here would not be visible because 2 is taller than it, but 5 would be visible from both sides because it's bigger than 0 and 2. Okay, yeah, that's the example. The top left 5 is visible. Top middle 5 also visible. The left middle 5 is visible, but only from the right because all of the other trees to the right are shorter. But the one at the bottom, there is another 5, and so it looks like it still wouldn't be visible. Okay, so with 16 trees visible on the edge and another 5 in the interior, a total of 21 trees are visible in this example. So we can always assume that the ones on the outside are visible. So what we need to do is kind of iterate through further and further inside and just check at each point if each item is visible. We'll probably want to create a 3D array or something to map this. But yeah, let's just get started. I think the problem itself is easy to understand. The data set, there's a lot of numbers, but the rules are fairly straightforward. We're going to copy that over and start trying to figure it out. Okay, so for this data, we've got the trees in a perimeter, and any tree that is the tallest so far, either from left, right, top, or bottom, can be counted. So I think what we'll need to do is just traverse each way. So we'll have to go left to right on each row, right to left again, top to bottom, and then bottom to top. Now, any number of those paths, each tree could either be visible or invisible from the outside. So I think what we need to do is just create sort of like a reference, maybe like a map of the coordinates, and we'll just have to keep track, maybe set just flags for each position. So this would be coordinates, maybe 0, 0, and this would be 0, 1, 0, 2, and so on. And anytime we go over a pass one way or another, there'll be 4 total passes for each index or for each coordinate. If it is the largest so far, we will set it to to true. So let's go ahead and start figuring that out. I'll make a um, I'll make a 2D array, I suppose. Tree grid, it's going to be list of list integers. Actually, no, it'll be a list of booleans, right? Because these are the flags that we'll set. Um, and we will say it is a mutable list. Okay. So this is going to represent kind of when we're at the end, we'll go through and just count how many are true to get our answer. But for now, we need to write the logic to iterate over it. Or actually, we need to fill it first with values initially. So let's write a function to fill that tree grid. Filling the tree grid is going to take our input list of strings, and it's going to have a tree grid, which is our list of all of these. Now they're all going to be initialized as false to begin with, and then we'll update them as we go through the program. So here we will say fill out the tree grid with, actually we could just start it like that. Fill the tree grid and give it the input, and then we'll just return this list. Okay, so something like this. Say it's a list of okay, and our input we'll say for each line. So we have our input, each of these are a line. We've got 99 lines. So each time we get a new item, that will be how our list kind of is represented. So we would say tree grid add, and this needs to be a mutable list as well, because we'll add a new mutable list of, and it already knows the type that we're looking for, Boolean there. So at the end, we will return the tree grid, and now what we need to do after we've added it is we actually need to go through the string, and for each character, we need to add the tree grid. We need to add all the trees for it. So let's see, input. This is going to be a line is our first iterator, and then a character in the string is going to be there. Let's update this, and we don't need to know the character right now. So far so good. It says we could do a repeat here, which is probably true, because we're not using the value from it. So this should give us our grid of all false. Let's just look to make sure that that's about right. Oh, I need to do day 8. Okay, so let's debug that. Just make sure that we got a good value. The next thing that we'll need to be doing is checking left to right and top to bottom. Um, yeah, so let's do that. We'll check right to left and left to right. These are probably going to be mostly duplicated. I'll see if I can condense them once I get the logic sorted out. Um, okay, so we return and our grid is 99 height, which is good. And then there's inside of each one, there's 99 characters and they're all false. So that looks good to me. Okay, so down here we're going to be checking top to bottom and bottom to top. And what that's going to do, each time it does a check, it'll update the tree grid. So we'll make that a parameter for each of these. Tree grid is going to be a mutable list of Booleans. Okay, and so after we run through each of those, we should be able to just have our answers. So let's set our logic up like that. Check. Um, do this and check left to right. Copy those over and we'll do top to bottom and bottom to top. Yeah, once we have that, we should be able to return tree grid. Okay, so now what we need to do is, okay, I'll rename this. So we have just a line. And so for each of these, we just need to do the logic of going through. So tree grid, oh, we need to have the input as well. So we'll have our input, which is a list of strings, and the tree grid. Okay, so now I think we're ready to just write these out. They should all be the same, just with a little variation. So if I'm going right to left, I'll start left to right actually. So left to right, I'm going to take the input, let's say for each, which is going to be coming top to bottom like this. And for each one, I'm going to iterate across. So this should be the most straightforward because inside here, I can just go like this. We're taking a line and then the line for each, just like that. So we will say the tallest tree so far that we've reached is 0. I wonder what the size is. So yeah, there could be trees of 0. So we need to start this counter actually below 0 or else it won't count the perimeters. So then we can say if tallest tree, or if it as an integer to int, why doesn't that work? Is greater than tallest tree. Why is this deprecated? To int. To int. Okay, I think it's saying to use the code, but if it's a character, I think I can assume that the code should just be the number. I want to double check though. We'll just write this out and then run it. So if our current tree that we're checking is taller than the tallest tree, then the tallest tree becomes this one. And then we would set this one as true in our grid. So that would be tree grid line. We needed to do these indexed. So for each indexed, we'll do the index in the line. And then for this one, we'll do the same for each indexed. And we'll just say index and the character. So then we can redo that, character. Okay, and once we're here, this is where we will assign in our grid. So the index, oh, we need to name these separately. So this would be line index. We'll just, for simplicity, we'll just make this the X and Y. Or would it be Y and X? Sure, let's just stick with that. Equals true. So that should kind of get us mapped out a bit. But I'm curious why those weren't working or I'm curious why this is deprecated. I'll take a look in a second. Return our input for each of these. And we'll see what we get. I'm going to put the breakpoint in there and just see what this comes out as. So the character is it's a 2, but the code is apparently 50. Oh, you know what? Maybe I just need to change this to a string first. I bet that's all I need to do. Yeah. Okay, right. So let's try that again. That's what we get. So just run this here and see to string to int as should give us a 2. Yep. Great. So now when we hit our next point, tallest tree should be 2 and it stays 2 until I get to a taller tree. Now it's 3 and there we go. So logic looks good. I can't think of anything that would be wrong with this at this point, so I'm going to I'm just going to copy this over and do it for each of them. So for left to right, from right to left, we are going to take line, we're going to reverse the strings. So that's going to take us, instead of left to right, that'll take us right to left. And then from here, we'll need to do something differently. So instead of coming down like this, instead of coming down one at a time, one line at a time, and then zipping all the way across, we'll need to sort of flip it. Because we already have our inputs in these lines, we can just take the first one from each, yeah. So we'll just make a separate iterator over the top, which is input, we'll take the first length. That's going to be how like far across horizontally we need to go. We'll just repeat that. And then when we put our input inside of it, we're just kind of like doing some of this backwards. So now the first thing, this is going to be our X value. And now this is going to be our Y. And the line will be, the character is just going to be the index of X. So our line taking X will be our character. Okay, and I think that's the right idea. And we'll do the same thing down here. But this way we're going the bottom to the top. So again, we will just reverse this before we get started. Okay, I think that's about right. I'm going to set a I'm going to set a breakpoint here and just see what the tree grid looks like after processing all those. Okay, we got a breakpoint here, so we'll skip that. So when we get over here, what does the tree grid look like? We got a good mix of trues and falses. So I'm just going to take a look at how this should, I'm just going to do some spot checks. So for here, the first item in the first list should be true, because that's this one. The second item in this list says it is false. So that's this one. That should not be false because it is so far the tallest. So I messed something up. Yeah, I see what the problem is. So in this logic, for each line that we're going through, we're not clearing out the tallest tree. And that's a problem. So like if the tallest tree in this row is like 8, it's still gonna say 8 when we get down here. Yeah, so that's just what we want to do, is clear out what is the tallest tree at the beginning of each iteration. So yeah, we'll just put that here like this. That way it doesn't persist across what we're doing. I think that'll give us some better results. Okay. Okay. So now I'm going to run this and let's see what we get one more time. Okay, so in our tree grid, again looking at the list, we have all of these are true at the top, and that would be correct, because if we're looking across here like that, they would all be true. It wouldn't be until we get to the second list that the first one is true, and then other ones might not be. So here we have true and true. I'm not sure if That's correct, because this one would be, it's saying that 0 is visible. Yeah. So I'm going to do something else here. I'm going to just try with the example input so there's not quite so much to look at. I'll just copy this. This input, let's run it to get our answer and see if it matches what was in that example. 19 is what I got, and the answer was 21. So something's still not right with the logic. Now I can debug it to see why. Okay, so looking at this, the first row would be here, and they should all be true, of course. The second row, the first one is going to be true, second one's true, third one's true. This one would not be, so I think that lines up. The one at the end is true. For 3, that'd be here. This one's visible. This one should not be visible. Oh, that's not the one we're looking at. We're looking at this row. So 6 would be visible, 5 is because of the right side, 3. The middle one should not be, and that's what it shows here. And then the second 2 would be. Okay, so then our row down here, this would be true, yes. 3 would not be, so that's false. 5 is true because it's at the bottom. 4 would also not be, but the last one would, so this one's correct. And then at the bottom row, they should all be true. So that's where I'm missing my 2 is, I think the bottom to top isn't working. And why could that be? Because it should be doing the same as the other ones, bottom to top. You know what? Actually, I bet it's because when we reverse these, the grid, we're going backwards. So when I'm reversing, y is assigning it to the wrong space. So here, yeah, I think I need to offset this. If I go for the input size and just subtract that, that should give me the offset since I'm counting from reversed. The first index should actually be the last index. And I'll probably have to do that up here too for y as well. Maybe it would be x, because that's what's reversed. So x, we'll do the line size, length, minus that. Let's run it. We should get 21 for the example. Oh, out of bounds. Oh, right, because the length, yeah. So we need to subtract 1 from the length as well. Same here probably. So now let's run it. Okay, great, that was the problem. So I'll just go back to our actual input text and run it there, and I think that should get us the right answer. So 1776, I'm going to copy that, and we'll give it a shot. Great, that's the right answer. Okay, so we got one of the stars. Let's move on to part 2. So for part 2, content with the amount of tree cover available, the elves just need to know the best spot to build their treehouse. So they would like to be able to see a lot of trees. We want to measure the viewing distance from a given tree. To measure the viewing distance from a given tree, look up, down, left, and right from that tree, and stop if you reach an edge or at the first tree that is the same height or taller than the tree under consideration. So if a tree is right on the edge, at least one of its viewing distances will be 0. So the elves don't care about distant trees taller than those found by the rules above. The proposed treehouse has large eaves to keep it dry, so they wouldn't be able to see higher than the treehouse anyway. So in the example above, let's see, the middle 5 on the second row here, looking up, its view is not blocked because it's free. It can see one tree, which is 3 high. To the left, it's viewing blocked immediately. It can only see one tree that's 5 trees, or that's the height of 5. To the right, it's not blocked, so it can see 2 trees. And looking down, its view is blocked down here, so it can see 2 trees as well. So a tree's scenic score is found by multiplying together its viewing distance in each of the 4 directions. Okay, so we just need to look up, down, left, and right, see what the score of the trees are until it hits one that it can't see past. Take that count for each direction and multiply them together. So this one was 1 times 1, 2 times 2. However, we could do better, so we want to find probably the one with the highest score. This one has better viewing, so that's 2, 2, 1, and 2. Okay, so what's the highest scenic score possible for any tree? Great. What we need to do then is just update our calculation. We already have a map of these. So now we just need to do the calculation. So part 1 is already done. Let's see. Part 1 is done. So I think what we could do here is probably, yeah, just copy this over to part 2. We're still going to fill the tree grid, but instead of just a grid of true and false of if they can see the border, we need to see, we need a map of their heights. So we'll need to edit this to maybe do it a little bit differently. Yeah, okay. So I'm going to reuse that example and just try to calculate our new challenge on that. So what I would need is, instead of a map of true or false, I'll need to create that same map just with the height of each tree. And then checking each of these will kind of work the same, except, yeah, the map should be actually how far it can see to the left, right, top, and bottom. So we'll need to make it probably a data class, and we'll just store that instead of the booleans. So data class viewing distance. It's going to be a value of the tree's height, and then it's going to have top, bottom, left, and right. So by having that mapped out into a class like this, we can easily just kind of perform the same checks, but do something a little bit differently. For my code, I want to preserve the same solutions for part one, so I'm going to just make another function for filling the tree grid um, for viewing, and instead of returning this list mutable booleans, it's going to return for the viewing distance. Okay, and tree grid, we'll just update that and say it's the viewing distance. And this is what we're going to call from here for viewing. Um, okay, and instead of adding just false to pre-populate these, we will create a viewing distance and just say that each of these are initialized at 0. So then here we are creating the viewing distance. And then when we go ahead and check across each way, we'll need to have a little bit different logic. So I'm actually going to put all the part 2 stuff at the bottom, like this. And up here for part 1, all these helpers, I'll say just region part 1. And yeah, because we'll end up having a good amount of code here. All right. So we'll still need to copy each of these functions and kind of do the logic the same, but then just edit them. Instead of just counting which one's the tallest, we're going to need to do it a little bit differently for viewing. Let's add that onto each of these. Okay, and that's what we will do in our part 2. Logic, right to left, viewing. Okay, and it is going to take this type with the viewing distance instead of the Boolean. Great, and tree grid, what do we need to return? We need to return the product of multiplying those out. So instead of returning a sum of something, we are going to return let's see, tree grid flatten. That's going to take the two lists because once we've gone through them, we don't care about their positioning anymore. We just want to have a list of all the possible trees, and we will say the max of the sum or the product of these. So get viewing score. We'll make that a function on viewing distance. We'll say get viewing score is an integer, and that will return top times rest. Okay, so once we have this, we can get the viewing score. And I'm going to collapse part 1 region. So here's what we have. At the end, we're going to take every single tree and just take the max of its viewing score. So then for each of these functions, we just need to actually go ahead and just calculate that out. So how would we do that? Yeah, let's take a look. So we're still going over the same way. Okay, so for this, what we might actually have to do, instead of just tracking the height of each tree and passing in a score of like top, left, bottom, right, we might just have to keep a list inside of each tree as we go up. So if we start here and we're going down, we can keep a list of each tree so far and just add that as we're going down. And then it'll be the same value, so it'll be the top for each of these, but the list will continue to accumulate. I think that's what we need to do here for viewing distance. So the top is going to be a list of integers, and it can just start as an empty list maybe. We'll do that for each of these. Okay, and then we'll need to do something different for this calculating the view score. This is where we will need to add logic for stopping at a tall tree. So we'll figure that out in a minute. For now, just going to skip that. We need to set up these functions to fill these values. Yeah, okay. So that's what we'll do. And here we already have the viewing distance since it was initialized as just these empty values. So what we are going to want to do is either make these variables or let us create lists. I think we can say they're just variables. Yeah. So then for each of these directions that we're going, we will need a list. So instead of tracking the tallest tree, we will say trees is a list of integers. You get a mutable list. So as we go along, it doesn't matter if a tree is taller or shorter than another one. So for each, we're just going to say, we're just going to add to it the that value. So this is the tree height. And then we will say that for this tree grid value, and we already have that figured out for these, we'll say that the left, because we're going left to right, so as we go along, we should be accumulating the trees to the left, and we'll just say trees. I think that kind of makes sense, so that by the time we're done with these, we should have all of these filled out, and we don't even maybe even need to know the height of the tree itself. I don't think that matters. I think we're only, for each tree, we're just checking the directions beyond it. Well, no, because we need to know, yeah, we need to know what height this one is. So right, that makes sense. So we'll want to edit that a little bit because we want to set the list of trees to the left before we add this one to it. because this tree shouldn't be included in the trees to its left. We will also want to set this one's height. So we'll do that same. Height is going to be, we'll just create a height variable for it, which is here. And we'll add to the height, and height is equal to height. And this isn't a variable, but it needs to be. Okay, I think we're just about there. So this doesn't need to be a variable, but yeah, that should work. And just for simplicity, I'm going to make this a scope function. So apply will let us just call these things inside the block together like this. Okay. And height. Okay, so let's go with this. Say this. There we go. Okay. Now I just need to copy that same kind of pattern over for each of these other ones. Let's try to run this and just see if it's populating these correctly. I'm going to put a breakpoint up at part 2. What we should have is a grid that kind of mimics this. So if we look at the tree grid, first one, first item, viewing distance, that's this corner one. The height is 3. There are no items to the top. No items to the top. There should be some to the bottom though. Left is the only one that's still applied, and you know what, that's probably going to be the same for all these. Left is the only one that's there, and that is because we just because I copied these all. So instead of left, these should each be different. So when we're going left to right, we're accumulating the left values. When we're going to right to left, we are accumulating right values. When we go top to bottom, we're having a trail of the top values. And in the other case, we're going bottom. Okay. Now let's try rerunning that. Okay, so looking at our grid again, this is a little more what I would expect. So for the first one, the height is 3. The top has 3, 2, 6, 3, and 3. But it shouldn't have anything. And that's because it's counting from here all the way down. Yeah, that doesn't really make sense unless the lists that we're tracking aren't resetting when they should, but yeah, let's see. So trees should always become a new list. It would start as an empty list, so if I'm starting from left to right, the first value should just get an empty tree list. I'm not sure why it wouldn't. It looks like that's the same for all of these. Okay. Might have to debug and see why that is. For each line, we'll just set it here and go through. So we're going left to right. Our tree grid should be empty. we already went right to left, I think. So this one's tree grid it's empty on the left. If we run it again, now there's a 3 on the left. And when we go again, we are going each character across. Okay. So now there's a 3 and a 0, and it's just going to keep adding up 3, 0, 3, 7, 3. But this same item shouldn't keep getting those same amounts, except, oh, right, that makes sense. Right. So as we go, we're updating these. We want to make this a new list. By making it a to list, it is no longer going to update the previous values, because we're assigning the same list basically all across the way, and then we're updating that list, and then even though we've already given it to those other objects, they're getting the updates. So we just need to create a new list for each of these. I think that'll solve it. Yeah. Tricky. Okay, now when I debug, each item as we go along should be getting a larger and larger list. So right now, yeah, that's what we're saying. So it starts with empty and then it grows. And that's what we'll see happen here. Yep, empty, 3, 3, and 0. Great. So I'll debug the final result. I think we pretty much have everything we need except the logic in calculating at the bottom this, getting the score for each item. But looking in the grid for our sample, the top left position, so here this has a height of 3, there's nothing to the top and there's nothing to the left, but to the bottom there's a 2, a 6, a 3, and a 3. Now they are backwards here. So I think we need to reverse these before we add them in at each point, because right, we started at the bottom, so we added a 3 and then we added the rest, but by the time we get to this one, they should be in order of what's the closest. So I'm going to do that quick and then start working on the calculation for the viewing score. Anytime we add the trees, we should be taking it reversed. And that will always give us the closest first. Okay, and I think reversed actually is going to return a new list anyway, so we might even be able to skip going to list. Yeah, but I'm going to leave it for now, just because that's how it went. So then when we're here getting the viewing score, this is where we need to trim after the first tree that we run into for each list that is as tall or taller than our tree, right? Because in the example here, 5 to the left, it's blocked, so it can only see this one tree. Okay, so we need to include the tree that's that height, but we just don't include anything past it. So that's what we would do here. For getting the viewing score, we are going to take Um, Maybe we can make these mutable lists. Actually, we'll just leave them like that. So top score equals top to mutable list. And we need to be able to drop all at the end. We need to get the index of the first tree that's as tall or taller than this one. So that would be top first, index of first, where it's top is just integers. So that would be where it is greater than or equal to height. So if this is the first index, for example, looking at our input, if this was the one right next to our item, what we need to do? We're going to want to drop the last amount, not the first, because we want to keep the first items that we can see. And if we get an index, it's going to be starting from the beginning. So we would need to take the size minus that index, and that should give us how many to drop. Yeah, I think that gives us each. So really, that's not a score, that's still the list. Top visible, and we're just going to do that for each side. Top, bottom, left, and right. So this will be how many are visible in each direction. And I should be able to debug this just to see if that makes sense. Okay, so here it's saying that there's none really visible. Oh, I did the top for each, so I need to update this. Okay. Bottom. Now let's go through that. So here's the sizes. This is a height of 3. I'm guessing this is our first item. So what that would say is that there are, well, we can look down here to the top, there's none that are visible. To the left, there's none that are visible. To the bottom, it says there's 1, but there's actually 2. And same thing to the right. We can see the tree that's the same size as us, we just don't want to see past that. So we need to cut 1 off of what we're dropping. So this is this. We're gonna just remove 1 from these, and that should include at least the one that we can see. Let's debug again. So now, yes, that works. So for this one, we can't see any to the top or the left, but we can see 2 down and 2 to the right. If we go to the next one, this one is height of 0, so it must be this one here. So to the left, we should be able to see 1. The bottom, we can see the 1. The right, we can see the 1, and the top, we can't see any. Great. Okay, so I think we can get the score for each of them now. Then all that's left is to multiply them together, and we'll do that here. Top visible And is that the number? Number of trees? Yeah. So it looks like we were just doing that. And we probably just need the size then. So there we go. Top visible. Now we just need to update to use these values. I think that'll get us there. I'm going to run this on our sample data for part 2. It says 3. That can't be right. It should be 8. Okay. So why would it be 3? We'll say total visible is this. Okay. And we'll return that and debug to see what it looks like. So here, the size of these, empty size. So there's 2 in the bottom that we can see, and there is 2 on the right that we can see. So why is that not working? Is it because we are multiplying by 0? That makes sense. So total visible would be 0. That's going to be the same for all the items at the top. So once we get into some of the other areas, yeah. Yeah, something's just wrong with this logic for dropping. So I guess I'll run through it. For top, there should be at least 1 visible. So let's look at this. Okay. One at a time. So the index of the first, where the height is equal, without dropping any, that's what I'm going to look at, is the index of the first. It's a -1, and that's probably why. -1, so yeah, I might have to split these up a little more and only drop if there is a number. So we're going to look at the index of the first, where the height is equal to or greater than our height. Then we're going to let, and if the index is -1, we will just return the top, because that means it didn't find any, and so it doesn't need to drop any. Otherwise, we will drop the last and return the size. We're going to return the size down here instead of up here. And we don't need to get the index of the first because we already have it in here. And we know that we need to subtract 1 when we're dropping. So yeah, we don't need to make this a mutable list yet. So we're going to say top, it's a mutable list, and then drop the last. So that should be more accurate. Doesn't look quite as good. But that's what we got to do. So I'm just going to rewrite these real quick. Great. I think that's what we had going wrong the first time. So what do we have? Top, bottom, left, and right. Let's run this again and see how we did. The top row is still going to be the same, so second, third, fourth, and fifth. So the second row, the first and the second item. And now it looks correct, where there's 1 visible on each side. The value is a 5. So for this one, there's only 1 to the left, 1 to the top. The right is the same size, so just 1, and the bottom is the same size, so just 1. When we move over 1 to the next 5, we should have better viewing distance now, because this one can see 1 up, it can see 1 to the left, 2 to the right, and then 2 to the bottom. Yeah, so that's more accurate. If we actually run the program, we should get 8, and we did. So I think, yeah, there's 8, so I think we're good now. Shouldn't have to debug. We can just put our sample sample text back. All right, let's run this. And this is our best viewing distance. Let's check it. And we got the answer. Good. So the elves have successfully found the best place to build their treehouse in the forest. I got a little off track today, I think, with just some of the logic towards the end, but overall, debugging is really helpful there. And yeah, I'll just clean up some of this code and push it up in a bit, but that's it for today. Thanks for watching.